Let's talk about potential energy, specifically potential energy functions. We've left this with the work kinetic energy theorem, where we have one type of energy. Everything else is an external force that can do work on our system and change that kinetic energy. So consider for a moment a pendulum. This pendulum can start elevated. We can have work done on it. So gravity does work. And it winds up speeding up. So we have some kinetic energy. And then gravity does negative work. So it slows down. And then it swings back, right? Going this way. It's going down again, so gravity does positive work. It's moving at the bottom. It goes up, so gravity does negative work, and it slows down at the top. It seems like this kind of keeps going back and forth, and in an ideal world, this would go on forever. Ideal meaning, with a vacuum and no air resistance and no collisions with anything and all sorts of stuff. Now, maybe, just maybe, there's a way to describe the energy of this ball in terms of its state as opposed to its path. So talking about its energy because it is here at these endpoints instead of because of the work that's being done as it goes down to the bottom. And in fact, this should be familiar. We talked about this, and you should know we're just talking about gravitational potential energy, that when the ball is higher up, it is a higher gravitational potential energy. So we chose to ignore this and just talk about work, because work is a general thing. Only some specific forces can give rise to a potential energy. And so now we're going to give rise to one, a nu g, which is going to be, it's a function of the position of the ball, specifically of its height in this case, really. We're going to say that the change in gravitational potential energy is going to be the opposite of the work. So, in this case, when the ball is going to the right, and we're having negative work, or we're having, positive work, that is a negative change in potential energy. The ball is lowering. When it continues to swing to the right and the gravity is doing negative work, we're going to say that's an increase in gravitational potential energy because the ball is going higher up. So that's how we're going to reconcile these. We're going to define it entirely in the same form. Still, we can still think of it as the ball as gravity doing work, the Earth doing work on the ball, or we can think of it as the energy of this ball-Earth system as changing. So in general, if we have some conservative force, some path-independent force, so we can define a state function for it, because the system is so arranged, because the spring is stretched, because the ball is elevated, there is energy, then the change in potential energy is going to be the opposite of the work done to achieve that state. Because it doesn't matter how it got there, it only matters how it started and how it ended. I could have raised and lowered that ball 1,000,000 times. That pendulum could have gone back and forth 1,000 times. It doesn't matter. It only cares where it starts and where it ends. That is going to dictate what happens gravitationally. So now we have this new and improved work energy theorem, where instead of work causing a change in energy, kinetic energy, it's going to cause a general change in energy. So that general energy, that total energy, is going to have a kinetic term, it'll have a gravitational term, it'll have an elastic term, it might have an internal term, it might have an electric term, it might have a chemical term, it might have a whole bunch of terms. We're going to mostly focus on just these three. And this is what we're going to usually call the mechanical energy of our system. So another way of looking at this, we have, our mechanical energy, plus a whole, any other terms that we might have, plus our work. So the initial state plus our work is equal to our final state. This is just our usual statement of a conservation law, that energy is conserved unless it's changed. But if it is changed, it's changed, we can track it. You can't create energy, you can't destroy energy. You can't magically have more energy. It has to have come from somewhere via work. So just quickly, how did we get here? If we start from the work kinetic energy theorem, which we had somewhat justified before, I can say that this work maybe has some conservative forces. Any conservative force I can break out and talk about the work done by that, and then work done by non-conservative forces. I can then kick all of these conservative terms over to the other side, and then, oh, look at that. I so carefully defined the change in potential energy as the opposite of the work. It's almost like I knew that was coming. Physically, this is really just a question of something being outside of our system and thus able to do work versus inside of our system in order to have an energy in our system. That minus sign is basically allowing us to switch from inside to outside. It's a matter of perspective. Now, we get a little more than just a minus sign from this. So let's say we have u of x for some generic energy. So better yet, we can define an energy function in all of space that is only a function of the position. So this means that, maybe if we're writing code to try to simulate something, or if we're trying to explain a really complicated setup, we might not be able to figure out exactly what the potential is because of all of the interactions, but maybe we can figure it out by putting test particles there, or by putting test charges, or by, experimentally kind of figuring out, at this point right here, I know that the energy is that, and then, figure it out next to it and kind of smooth out a curve to get this function. So let's say we have this. There's a couple of things that are going to be interesting. One of them is going to be what we're going to call turning points, points where the mechanical energy is equal to the total energy. So let's say that I have an object and it has a total mechanical energy of this value. I don't know, maybe it's 1 joule or something. Whatever. It is, just E. So what happens here is that, at this point, this difference between and by the way, your potential energy can clearly be negative. So E, my total energy, should be equal to my kinetic energy plus my potential energy, right? Since I only have just one potential in this case, that's all that I've got for my total energy. So if my potential energy is really small, like right in here, this distance between my potential and my total must be my kinetic. So if I get to a point over here, I see I have less kinetic energy, and then eventually I get to these. These are the turning points that we had mentioned 10 seconds ago. The points where the total energy is equal to just the kinetic energy, or the potential energy, sorry. Total energy equal to the potential energy. You have no kinetic energy. It is a point at which you're going to turn. Also from this, the force is going to be the derivative of the potential energy. We can think of this because we can recall the force is, the work is the integral of the force with respect to position. So that means that the opposite of the potential energy is the integral of the force with respect to position. So the potential energy is the opposite integral of the force with respect to position. So if I, in a very fuzzy sense, take a derivative of both sides, I would just see, I guess I didn't need to move this minus sign over. If I take a derivative of both sides, I would casually see that the force is the opposite derivative of the potential. So how does that make sense? Let's say I'm down here at the bottom of this, I'm right here. And we have a little ball. I can think of this as a gravitational potential, maybe. If I'm at this point, I can think of this as serving as a hill. What is this ball going to do right here? Well, it has some kinetic energy, right? If it's going to the left, it's slowing down. If it's going to the right, it's speeding up. Whoops, I want my ball back. So it means it's experiencing a force to the right at this moment. If I look at this, the slope is negative. The opposite of a negative is a positive. So the force is it makes sense to some extent. Or at least it's consistent with, my claim is consistent with what I've drawn. Erasers are hard. All right, it's not happening. Now, this that I've drawn here is a special case where the energy is capped. It's less than both of those values. This is a bound state of something. What I've actually drawn here is an energy function that represents, to some degree, a molecular bond, where there is some distance in which the object is bound together. If this is instead of a position, it's a function of radius. This is some bond radius. If I get a little bit past this, I have to put some energy into it to break this bond and get over this hill. But then if it's over here, it's going to come in, and it doesn't have enough energy to get over this hill. It's just going to bounce back to forever. Or if it has too much energy, it'll just come in, just roll around, get back up to here at some turning point, roll right back out. I don't know. It's not really too important, but I like talking about chemicals from time to time. Chemistry doesn't win all of the fun stuff. So, point is, we're talking about conservation of energy, and our new shtick is this work energy theorem. This is just kind of a reformalization of the stuff we've been talking about before. The brand new thing is getting to talk about generic potential energy functions and reading these, and thinking about, what it means to be at different positions in here. You can always kind of pretend that this is a hill and that you're talking about gravitational potential energy as an analog because it works. But really, sometimes if it is an if it is chemicals and atoms that we're talking about, this is an electric potential energy or some other kind of nuclear force if you're getting even smaller scale than that. All right, hopefully this helps get you started.